remember what we did last time, but according to my notes, we were doing flips, right? Flips of triangulations. Okay, so flips of triangulations, and so as a reminder, we have a point configuration in R to the d minus 1 of points in general position. And what we figured out last time was that if n is equal to d, then these points form a simplex, the vertex of a simplex, so there is only one triangulation. And if n equals to d plus 1, then you have exactly two triangulations. In this case, A is called a circuit, right? And so in particular, both of these triangulations are regular. And we say that these two triangulations differ by a flip. All right? And yeah, so some examples, when d equals to 2, we can have 3 points on the line, and then the two triangulations, so this is A, and then the two triangulations look like this. And then if d equals to 3, then we have A could look like a square, in which case the two triangulations look like this and this, or A could look like a triangle with a point inside, and the two triangulations would be either just the triangle or a triangle with three triangles which together form the bigger triangle. So these are all examples of flips. And and by the way, let me mention in general how you should think of these pictures. And that it's related to the fact that both of these triangulations are regular. So you should think of these drawings as of projections of the lower boundary of some higher dimensional simplex. So in general, a flip, this is an informal statement, but a flip replaces an upper boundary of the d-dimensional simplex with the lower boundary. Where, so that simplex is not the standard simplex, but it's somehow embedded into the d plus 1 dimensional space, and then upper boundary with the lower boundary. And so if you look at these pictures, right, so yeah, maybe I should look at these pictures. Have a flip which replaces this triangulation with this triangulation, and what you should think of is there is a triangle living in one dimension higher, and you sort of project the lower boundary. You get this triangulation, and if you take the same triangle and project the upper boundary, then you get this triangulation. In particular here, if you draw a tetrahedron in 3D, these look like two boundaries of the tetrahedron, and similarly, depending on whether the one of the vertices of the tetrahedron projects in the middle of the other three, then you get either this picture or this. Does it make sense? Yeah. Of a simplex. Yeah, in general, no. Right. So I think in general, that's a good point. So in general, so how many facets does a simplex like this have? D plus 1. Thanks. D plus 1 facets. So the point is that whenever you apply a flip in any dimensions, all of these facets are going to participate in one or on one or the other side of the flip. In particular, here, delta 2 has 3 facets. So we see 2 facets. There's 1 facet here and 2 facets here. So 1 plus 2 is 3. Similarly, here you're going to see 2 facets and 2 facets. Here you're going to see 1 and 3. So they always sum up to 4. So d plus 1 in general. But yeah, the distribution can be uneven or it can be even. And I guess before I go on and talk about the flips, let me do one more example. So I want to see what happens when d is equal to 4. And d is equal to 4, so yeah, remember a is inside r to the d plus 1. A inside R3, and then the number of vertices is n is the number of points. N is equal to d plus 1, so it's 5 points. All right, so I have 5 points in R3. And I just want to draw some pictures of how can they look like. So, and again, right, remember they are in general position, so they span, like, finally span the whole R3. And yeah, so how can they look like? Nice. They can be in convex position. So they form vertices of a polytope. So how many polytopes with 5 vertices can you name? Square pyramid. Interesting. Any other? Okay, the triangular bipyramid. Okay. What are the flips in these cases? Let's say for the pyramid. Say it again, I can hear. Oh, so you want to just take the square and then you take the pyramid over the 2 flips. Interesting. Okay, let's try that. So indeed, I can take my pyramid and I can triangulate it like this, or I can triangulate it like this. So, and each triangulation has 2 simplices. So I have 2 plus 2 simplices in one flip, in one triangulation, and 2 simplices in another triangulation. There is 4. How many total faces should I get? 5. Right, I should get d plus 1. I already had 4. 2 plus 2 was here, right? I can't. This sounds sort of. I mean, this should be 5. Should be d plus 1, which is. So what's the problem? Not in general position. Nice. Yeah. Okay. So the pyramid, there's 4 points which lie in the same plane. This point configuration is not in general position. Not in general position. Okay, so actually, yeah, the only polytope the only generic configuration of 5 points in R3 looks like this, if it's in convex position. So, okay, how does the flip look like? Right, so you want to get a vertex in the center of the triangle. And that's actually So remember, we have this point configuration A, and we only consider triangulations of A, which are not allowed to use any other vertices except for A. So what's a flip in this? Okay, interesting. There's one triangulation that you just cut it into two simplices like this. We have two simplices here. Is there any other? Take the top and the bottom and the two of the vertices. Wait, so I draw like a plane through these two vertices? But wouldn't this plane have a vertex here? Okay. The dashed line can what? Hold on, let me draw the picture. All right, so what's the other triangulation? And by the way, let me mention, what should I mention? What is the, oh, I have 1 minute left. Yeah, let me not mention anything. It's just, well, let me still mention. So the four-dimensional simplex, if you only look at the edges, right, you look at the vertices and the edges, which graph are you going to see? One skeleton of the what? Hmm? Okay, and yeah, I'm just going to see the complete graph on 5 vertices. So yeah, and all facets of this guy should appear in the flip, and all edges should also appear in the flip. And as you know, K5 is non-planar, so it cannot be the one skeleton of a 3 polytope. Right? So what's the other flip going to look like? If you assume that this is a hint for you to. Hmm? Have a what face? Yeah, I can, because of the window, I can 10 faces. Oh, okay. I mean, of arbitrary dimension. How many facets should it have? Yeah, it should have 3 top-dimensional. Yeah, so how would you represent this as a union of 3 tetrahedra? And you want every edge of K5 to appear in that triangulation. I take the top and the bottom and then do what? Oh, okay, nice. All right, so I take my 3 tetrahedra is going to be taken top and the bottom, and then any 2 points out of these 3. So the picture is going to look like this. So I'm going to use this invisible edge here and then split the whole thing into 3 tetrahedra, sort of like this. So this is not a vertex, this is just a representation. So each tetrahedron has 4 vertices like this. This is a straight line. Right. Yeah, I'm out of time, so thanks everybody. Have a good weekend. See you all on Monday.